All right, we are going to talk about section 3.2 right now, solving quadratic equations by graphing. So let's start off by talking about, how to solve how to solve equations by graphing in general. And so what we would do there is, in this situation where we've got a linear function where the highest power of x is 1, what we would do is move everything to one side, so we'd minus 19x, and you get negative 10x minus 9 over 2 is equal to 0. All right, then we would take this part right here, graph it, and find the x-intercept. So I've done that here in Desmos. It's not a perfect or not a wonderful graph, but what we see is that we have an x-intercept at negative 0.45. If you solve that algebraically, you would find that you get negative 0.45 for the solution. So we'll just put a little sketch here. It's not really that big a deal. We get that x equals negative 0.45 and that this intercept right here is negative 0.45 comma 0. Okay, so we already talked about solving equations by graphing in that way, linear equations. We can also solve quadratic equations in the same way. And what we're doing here is we're graphing the related function. The related function is the part of the equation that actually has stuff in it once you've set it equal to 0. So in this equation, what we'll do to solve it is we will graph y equals x squared minus x minus 6, and we will find the x-intercepts. All right, so I have that in Desmos already, so I will show you how to do this on the graphing calculator, the TI-83s as well. So I have that here. And remember, it's pretty easy to plot some points just by turning that into a table. All right, so I've got negative 2, 0. I've got negative 1, negative 2, or negative 4, excuse me. I've got 0, negative 6. I have 1, negative 6. And then I got 2, negative 4. And somewhere in here is a minimum. You can see it there in the graph. You could probably tap it if you wanted to figure it out for sure, but you get something like this for your quadratic. So your solutions, the solutions to this equation, will be this value and this value. Those are called the zeros. All right, so let's highlight those points: 3, 0 and negative 2, 0. So our solution then is x equals negative 2 and should make sure that goes through 3. Okay, so x equals negative 2 and x equals 3. In other words, when we solve an equation, we are finding the x values, or the x and y values, but in this case the x values that make the statement true. Okay, so what numbers can you put in for x that will make the left-hand side 0? Well, if you graph that part of the equation, if you graph this function, and you find the zeros where the function is 0, that is what will make the left-hand side 0, negative 2 and 3. If you plug in either one of those, you will get 0 on the left. In other words, you will make a true statement. That's what we mean by solving an equation. Okay? So I'm not going to go that in depth on every problem, but that is a technique for solving equations. Get everything to one side, graph it, find the zeros, which are effectively the x-intercepts. Which leads me to the next point here, some vocabulary. All right? Let me give you standard form of a quadratic. It is this: y equals ax squared plus bx plus c. We may have even talked about this yesterday. All right, so this is standard form of a quadratic. Given that, roots are the solutions to a quadratic equation. So if this was set equal to 0, so if it was in the form ax squared plus bx plus c equals 0, right, then the roots are the solutions to a quadratic equation. We found the roots to this equation. Why are there two names for it? Honestly, I don't really know. But you're going to see that vocabulary come up in the book. Excuse me, so I think it's worth mentioning here. Zeros. These are values that make a quadratic function 0. Graphically, they're the x-intercepts. All right, so you can see here on the next vocabulary term, the x-intercept are the points where the function crosses the x-axis. That's also where the quadratic function is 0. So when you see the words roots, solutions, zeros, and x-intercepts, all of those things graphically are going to be at the same location or locations. All right, let's take number 2 and solve that one graphically. So what we'll do, notice that this is not set equal to 0. So we're going to move everything to one side. I like having a positive x squared. It doesn't really matter though. So I'm going to first add x squared to both sides. So I'll get 14 is equal to x squared minus 6x plus 23. And then I'll subtract 14 from both sides. So I'll get 0 is equal to x squared minus 6x plus 9. And then I'm going to graph this part and find the zeros so that I can solve the equation. So in Desmos, it's fairly straightforward, and I will also show you how to do it in your graphing calculator as well. So let's look at this. X squared minus 6x plus 9. Where are the zeros? Well, there's one. It's right there at 3. Okay. If you're going to do this in your graph and well, I guess we should write down the answer here. So here's what the graph looks like. Dot at 3. I'm not super picky. We're just trying to use the graph to solve it. So x equals 3 is the only solution. Okay. In your graphing calculator, you go and go y equals, and then you will take and write x squared minus 6x plus 9. Take a look at the graph. Oh, my window is all messed up here. Let me just zoom 6 real quick. So here's the graph. Now, in your graphing calculator, to find the zeros, what you're going to do is you're going to hit second, the trace key, or second calc. We'll hit 0. It asks you to pick a point to the left of the 0 and a point to the right. So we make sure we get to the left of the x-intercept. Remember, zeros and x-intercepts are effectively the same on a graph. So we hit enter to the left of the x-intercept. We hit enter to the right of it, and then we take a guess. Hit enter where it's sort of close to that point. And we get x equals 3. Okay, again, ignore the rounding there on the end. Okay. Real quick, it can be a little bit harder to find the zeros when the minimum isn't on the x-axis. So if it's not, I just made up a function here. This is just minus 6x plus 5. If it's not, hit second calc 0, and you have to find them one at a time. So if you hit, you'll want to find the left bound, so hit enter. Get to the right of the 0 that you're trying to find. I'm trying to find this one here. Hit enter, take a guess, hit enter, and it will find that 0 for you. Okay, and then you'd have to do the same thing again for the one on the right. So it is definitely more work in a TI-83. All right, let's talk about this key concept box real quick. A quadratic equation can have one real solution, two real solutions, or no real solution. And again, these solutions are showing up as intercepts in the graph. So you can have one x-intercept, as we've already seen. You can have 2, which is very common for quadratics. Or you could have none, right? So you'd have a quadratic that's above the x-axis pointing up, or you could have a parabola below the x-axis pointing down. You wouldn't have any solutions, right? So just important to know that and be aware of the possibilities. Your book will sometimes say, find the consecutive integers that contain the 0, for like when the 0 or the root is a decimal. Ignore that. Always find approximate roots, which means always find whatever the decimal is, okay? So that's just something that when you see that in the directions, you want to know that you're actually going to just find the decimal. You're not worried about finding consecutive integers, okay? All right, let's do a couple word problems. Use a quadratic equation to find two real numbers with a sum of 15 and a product of 36, or 63. So when I see a problem like this, I'm thinking, okay, two real numbers I'm trying to find. There are two unknowns. They're probably different numbers. So I'm thinking x and y. What do I know about them? Well, their sum is 15. So x plus y has to equal 15. What else do I know about them? Their product is 63. Okay, well, that means that x times y, the two numbers multiplied, has to equal 63. All right, so I have two equations, two unknowns. What I'll do is solve one equation for x or y and plug it into the other equation. So I'll just take this first equation and solve it for y. You could have done it the other way. That would have been fine. And then I'm going to take this 15 minus x and I'm going to plug it in right here. So here is the equation that I get. X times 15 minus x equals 63. Okay? And then I'm going to solve this equation by moving everything to one side and graphing the related function and finding the zeros. So x times 15, x times x, that'll give me 15x minus x squared equals 63. I'm going to move the 63 over to the left so I get this. 15x minus x squared minus 63 equals 0. And then I'm going to graph it to find the solutions. So let's hop over to Desmos. And I'm going to put in 15x minus x squared minus 63. As you can see here, there's no solution to this equation. So that means that there are no two numbers that add to 15 and also multiply to give you 63 because there are no x-intercepts. Okay, so this one is no solution. All right, last one. A golfer hits a ball from an elevated tee box 200 feet above the fairway. The ball's height above the fairway is modeled by that function. How long will it take the ball to hit the fairway? Okay, so you might want to try this on your own first. What you're going to do is you're going to graph the function. So we'll go negative 16x squared plus 28x, excuse me. You do the same thing in your graphing calculator, replace t's with x's, plus 200. All right, now I have a problem. I cannot see the maximum here, although we don't really care actually. But one thing you can do is change the y-axis to go up to, I don't know, 500 maybe? Let's see if that's enough. Yeah, that's enough. Okay, so you can see that the maximum height of the ball is 212 feet. All right, and that actually turns out not to matter that much because what we want to know is how long will it take the ball to hit the fairway. Again, let's understand what's going on in the curve here. We have height on the y-axis and time on the x-axis. Okay, so when the height is 0, that's when it hits the fairway. So how long does that take? Well, if you just tap, you see that it takes 4.5 seconds approximately. So we'll write in fact, let's always go 2 decimal places. So 4.52 seconds. And if you want a little sketch of the curve here, then by all means, go ahead. Obviously, the scale on the y-axis is not ones, right? So 4.52 seconds is how long the ball is in the air, how long it takes to hit the fairway, right? And that's, again, just an application of finding the zeros of the function. And that's it for section 3.2.